Okay, so let us now generalize from perceptrons to a richer class of neural network models. Perceptrons, they had only one output unit. I mean, the perceptrons that we have introduced so far, they had only one output unit. Now we can generalize this to having multiple output units. Well, multiple output units could be plausible when you have a classification that involves multiple aspects, um, like if you want to attribute different features to an image, or if you want to to categorize a sentence into different labels, you might want to choose different output values. Another aspect is that we often code the output label as a one-hot vector, so it has exactly 1, 1, and the rest is 0. And this one-hot vector represents a certain class, for example, class number 3. So class number 3 could be an elephant, class number 4 could be an ape, class number 5 could be a cat. So then also you want multiple output units. So there's no additional technical difficulty from having an additional output unit. Basically, we can use our previous learning algorithm with some small modifications to also train such a model with multiple output units. What changes is a little bit of mathematics. Before we had a dot product between an input vector and a weight vector. So this was one vector multiplication. Now we can associate it with each output unit. We have one vector of weights. If we put these vectors together, we have a matrix, right? So we put the vectors together to form a matrix. Then we have a vector matrix multiplication, because the input stays a vector, and now we multiply this input with the weight matrix to get the pre-activation for each output unit. And then we put a non-linearity on each of these pre-activations. Now we can what is a bigger step, like going from one output unit to 4 output units is not a big step. We would still call that a perceptron. What is a bigger step is to introduce hidden layers. So, and this is a network that has hidden layers. So we have one hidden layer, 2 hidden layers, and this is the output layer. So what we could call in this network here, this is the input layer, this is a hidden layer, this is a hidden layer, this is the output layer. And these layers are connected by weight matrices. Basically, the idea is one stacks different perceptrons together, and if one does that, one has a multi-layer perceptron. Yeah, it's a perceptron with multiple layers. So this is more difficult in terms of optimization. So we cannot just use our standard algorithm that we have seen before, but we would have to do a more complicated approach. And this we will see in lecture 3. And what is the math behind that? Well, the math is also not very difficult. Well, the first layer it will compute, it takes the input, multiplies it by the weight matrix. So this is a vector. Then we add not a single bias, because now each output unit has associated with it a bias. So we have multiple biases. So we have a vector of biases. So we add that. And then we get a vector out of that. We put a non-linearity on top of the vector. We get the activation of the first hidden layer, right? So we get the activation of the first hidden layer. And this non-linearity is applied element-wise on the vector. And the second layer computes exactly the same. So it again has a weight matrix and it has a bias vector specification, but it takes as input the output of the first layer. So basically, this the output of here goes into that next layer. On a very high level view, what neural networks are doing, all kinds of neural networks. So we saw perceptron and then a perceptron with hidden layers, which we call a multi-layer perceptron, but they all do the same thing. They are mathematical functions. They are composite functions of the following form. They take an input, multiply the input by a weight matrix. So this is a linear operation. They put a nonlinearity on top of that, and then they feed that into the next layer, and again put nonlinearities on that, on top of that. And they could continue with as many layers as you wish. So X is the input, GF are the activation functions, W and V is what we want to learn. So this is what we want to change such that our neural network becomes good. And how do we want to change our neural network? So we want to change it in such a way that it optimizes or minimizes a so-called loss function. So in our case, we saw this squared loss function. What does that say? Well, it says I have data x, y. So x are my inputs and y are my labels for that input. So I have many such data points. And what I want is I want to have neural network predictions that when they have this input, they give an output that it is close to the true label of that point x. So that point x has a true label y, and we want our neural network not to deviate much from that true label. And this not deviating much is given here by the vector norm. Yeah, you have the vector norm where you have two vectors, you subtract them and compute the norm, and the bigger the difference between the vectors, the greater is the norm, and the smaller the difference, the smaller the norm. So we do not want to deviate much, and this much is also given as a sum, as an average over all points. Maybe for one point, okay, we can deviate a little bit, but then for the others, we should not deviate. Thetas are our parameters. This is our W and V above, right? This is what we want to modify and adjust in the neural network. And this modification and adjustment of our parameters theta, this is also called learning or training in machine learning. And this is a term that we will always use during this lecture. And to give a little bit more terminology and not to have any misconceptions, let's quickly look at some further concepts and names that you should keep in mind. So this is what we call the multi-layer perceptron, or would also call that, it's also called feed-forward network in the literature, because there's really a forward feeding of activation, starting from the input activation to the, that feeds forward through the network until we come to the output. That's what we call a node, like in graph theory. That's also a node. There are many nodes. Some nodes we call input nodes. And the first layer we call, and a set of nodes we call a layer. And that one here is an input layer. This is what we would call a hidden layer. This is also a hidden layer, and this is what we would call the output layer. That's what I said is an activation function on nonlinearity. This is a weight matrix that's consisting of several weight vectors, and an often used visualization of a feed-forward network is like this in blocks. Well, you just conceptualize all the layers, and this is called a multi-layer perceptron. And if such a multi-layer perceptron has no hidden layer, it's only called a perceptron. So the defining characterization of a perceptron is that it has no hidden layer.